All right, guys. In this video, we're just going to be discussing how to calculate average atomic mass, how it's calculated, what percent abundance is, what the mass number is, but basically how the average atomic mass, sometimes referred to as the average atomic weight, and a lot of times just referred to as atomic mass or atomic weight, how that's actually calculated. It's something that you need to be able to do. Essentially, it's just how to do a weighted average, something that's weighted versus just a normal average. And so we're just going to go through how to do it, and we're going to go through a worksheet that I got from Bishop Ayrton, just some different practice problems, and how to attack the different practice problems when it comes to calculating and using and the equation for average atomic mass. So for our VLOs, this would go with 2-2 when we start talking about the different isotopes that the elements have, and what that is, and how the mass on the periodic table that's given to you when you look at a periodic table, what that mass refers to. Okay, so the first thing to understand is the mass of an atom or ion. It doesn't matter if there's a charge or if it's neutral, is just dependent on how many protons and neutrons it has. And so to calculate the mass of an atom, it's just protons plus neutrons. Okay, so you always know the protons. If you know what the element is, then the atomic number on the periodic table is the number of protons. And then if you know how many neutrons you add, the protons plus the neutrons gives you the mass number. Okay, so when you see an isotope written this way in isotope notation with the name, the name dash the number, understand that that's the element carbon, and this number that's given is called the mass number. Okay, so you got carbon 12, you got carbon 13, you got carbon 14. So that means there's carbon atoms that have a mass of 12, there's carbon atoms that have a mass of 13, and there's carbon atoms that have a mass of 14. Okay, so if we go to our periodic table and we look up carbon, the atomic number 6. So that means every carbon atom has to have 6 protons. So if we go back to this list of isotopes, so if this is carbon, that means it has 6 protons. So how does it have a mass of 12? That must mean it also has 6 neutrons. 6 plus 6 is 12. But this carbon atom would have 6 protons and 7 neutrons. That's how you get a mass of 13, 6 plus 7. And this would be 6 protons, 8 neutrons, 6 plus 8 is 14. Right, so the difference in isotopes is the difference in number of neutrons. And that's going to change the mass because, again, the mass number is protons plus neutrons. So what we want to understand, though, is the mass that's on the periodic table is not the mass number. The mass that's on the periodic table, like for carbon, the 12.01 here, that's not the mass number. That's the average atomic mass, sometimes, again, referred to as the average atomic weight. Okay. Now, what that number represents is a weighted average of those isotopes that we just talked about, carbon 12, carbon 13, carbon 14, but it's weighted by their percent abundance. So if we go back to this note handout here, okay, notice that most carbon 12 atoms most carbon atoms are carbon 12 atoms. Notice they're almost 99%, 98.89% abundant. Okay, what does that mean? It means if I have a random sample of carbon, that means not around 99% of those carbon atoms is going to be carbon 12. So most of those atoms are going to be 6 protons, 6 neutrons. But some of them, right, will be carbon 13, and then some of them will be carbon 14. But it's going to be a very small amount of those numbers. So if let's say I had 100 carbon atoms, 99 of them would be carbon 12. One of them might be carbon 13, right? And that means 0 of that random will be carbon 14, right? So maybe it's, in a random sample of carbon, out of 100 atoms, you'll probably get 98, right? If you end up with all 3 isotopes, 98 of those would be carbon 12. One of them might be carbon 13, and the other one might be carbon 14, right? But odds are, a carbon atom that you might be studying right now, an individual carbon atom, odds are it's carbon 12, okay? But there are carbon 13s and there are carbon 14s. They're just much more rare, okay? So if it was a normal average, like carbon has 3 isotopes. If it was a normal average, the average of 12, 13, and 14, that would average out to 13 in the middle. And if they were all equally abundant, the average atomic mass of carbon would be 13. Okay? But what we'll notice is, again, if we go to that periodic table, that number on the periodic table, the average atomic mass is 12.01. That number is much closer to 12 than it is to 13 or it is to 14, meaning that carbon 12 is by far the most abundant isotope of carbon. Okay? So, an exercise you can do, it doesn't always work, but if you go to your periodic table and you go to that number, like so for nitrogen, the average atomic mass is 14.01. Odds are, if you round that to the nearest whole number, in this case 14, odds are the most abundant isotope of nitrogen is nitrogen 14. If we went to phosphorus, odds are the most abundant isotope of phosphorus is phosphorus 31, because 30.97 is closer to 31 than it is to 30. Okay? So boron, right? Boron has an average atomic mass of 10.81. That means its probably most abundant isotope is boron 11. But that's assuming that we don't know what the isotopes are. If we know what the isotopes are, then we can go to the number on the periodic table and figure out which number is this mass closer to, and that would end up being the most abundant isotope, because a weighted average is going to be closer to the number that's weighted more, that has a higher percentage. Okay? So the reason why carbon's average atomic mass is 12.01, which is very close to 12, is because carbon 12 is by far the most abundant isotope of carbon. Okay? So the way average atomic mass is calculated, here is the equation. You take the sum, that's what this symbol represents, the sum of the products of the mass number times their percent abundance. So you do mass number times percent, plus mass number times percent, plus mass number times percent. So you take the mass number of each isotope and you multiply it by their percent abundance. And you do that for each isotope, and then you just add them all up. That's all you do. So if we took this information that was given to us for carbon 12 and we calculated the average atomic mass of carbon based on this data, it would be 12 times that percentage, 13 times that percentage, 14 times that percentage, and then you add them all up. Understand, when you use the percentages in a mathematical operation, you got to convert them back to their decimal form. So you have to divide them by 100. So notice for carbon 12, I'm not multiplying it by 98.89%. I'm multiplying it by 0.9889. Okay? Now, if you wanted to, you could keep this number as 98.89. You could keep this number as 1.1. You could keep this number as 0.1. But then after you did all of that, then you would have to divide the whole thing by 100. Understand that if my mass numbers are 12, 13, and 14, when I calculate the average, it's got to be somewhere between 12 and 14. So if I don't get a number that's in between 12 and 14 when I do this calculation, then I made a mistake somewhere. Maybe I didn't, I didn't, maybe for this one I said 0.1 instead of 0.01. Maybe I didn't move the decimal place to the left 2 times. Maybe I only moved it one time. Okay, so, but that's all you do. So mass number times its percentage, plus the mass number times its percentage, plus the mass number times its percentage, you add them all up. So do the multiplication first and then add them all up, or put the multiplication portion in parentheses, and then add them all up, okay? And then also understand the unit for average atomic mass is AMU, which is atomic mass unit, AMU. Atomic mass unit. Okay. So that's kind of the background. Let's look at the practice we're going to be doing. Okay. So on this worksheet, it gives us a bunch of different examples. So what I want us to do is look at number 1. It tells us boron has 2 isotopes, boron 10, boron 11. Based on its atomic mass, which isotope is more abundant? So those are the 2 isotopes, boron with a mass of 10, boron with a mass of 11. So all we have to do is go to boron on our periodic table and see its average atomic mass and see what it's closer to. Is it closer to 10 or is it closer to 11? Well, boron's average atomic mass is 10.81. That's closer to 11 than it is to 10. And so therefore, boron 11 would be the most abundant. Now, if we needed to explain that a little bit more, right, it would be the average atomic mass of boron is 10.81. This would mean boron 11 is more abundant, right? And really, because they're just a one difference, it's 10 to 11, really, it's really easy to calculate what their percent abundances are. Boron 11 would be 81%, and boron 10 would be 19% abundant. So 0.81 and 0.19, but as percentages, boron 11 would be around 81% abundant, and boron 10 would be around 19% abundant. And if you did 11 times 0.81 and 10 times 0.191, and you added them up, you would end up with that number, 10.81, okay? So we'll keep on rolling. We'll go to the next one. All right, so here they gave us our mass numbers and they gave us our percentage abundance. So all we have to do is plug them in. Now, in this practice problem, the mass numbers they didn't give us were whole numbers. A lot of times mass numbers would be whole numbers. So instead of 31, this will be 32, and this will be 34, right? And this one would be 33. Okay, but if they give you the mass number like this and not a whole number, just use that entire number. So what we're going to do is this mass number times 95% plus this mass number times 0.67%, and then this mass number times 4.22%, and then we add them all up. Okay, again, use the percentages in decimal form, not like this. So instead of 4.22, I'm going to plug in 0.0422, and for this one, it's going to be 0.0076 when I put it in my calculator. All right, so if we look at it, here would be the setup. So I took the first isotope, multiplied it by 95%, so 0.95, that times 0.0076, and then that times 0.0422. You add them all up, and you end up with 32.057. My rule is we go to 2 decimal places. That's what they do in AP chemistry, and essentially that's what we do basically all the time. So when I calculate average atomic mass, I end up rounding to 2 decimal places because most periodic tables will have them listed as 2 decimal places. You can find periodic tables where they're listed more than that. So it's really just kind of what your teacher wants. So you might want to ask about that if I'm not your teacher, but if I am your teacher or you're doing this at West Springfield High School, round to 2 decimal places. Anytime we're doing molar mass or average atomic mass, which is the same number, just different unit, go 2 decimal places, okay? So that's 32.06 atomic mass units. And the other part of this question, they asked to identify the element. So what you would do is, usually we identify the element based on atomic number, but here we have the average atomic mass. Find the periodic table where that's an average atomic mass, and there it is. Sulfur has an average atomic mass of 32.06, so we can assume that the atom described in number 2 of this worksheet must be sulfur, or the element must be sulfur, okay? So now we go to this data table. Now remember, it's a weighted average based on the mass number, so the very first thing you need to do is complete this chart. So isotope A would have a mass of 204, 82 plus 122. So this would be 204, this would be 206, this would be 207, and this would be 208. So this is saying lead has 4 isotopes, and their mass numbers are lead 204, lead 206, lead 207, and lead 208. Now all we have to do is take those mass numbers and multiply by each of these percentages here. And here, let me get the hand. So we'll go this mass number times that percent, mass number times percent, mass number times percent, mass number times percent, and add them all up. And that's all we have to do. And I think I did it here on the worksheet. So yeah, first get our mass numbers. So isotope A was 204, isotope D was 208. Plug in everything. Now remember, I plug it in as a decimal. So, it was 1.37%, but that's really 0.0137 when I want to use it mathematically. Now, again, you could keep this as 1.37, you could keep this as 26.26, you could keep this as 20.82, you could keep this as 51.55, but then at the end you would have to divide by 100. Okay? And again, understand that if these are your isotopes mass numbers, then when I calculate the average atomic mass, it better be between 204 and 208. And it's probably going to be leaning a little bit more towards 208 than it is to 204, because 204 isn't that much abundant, but 208 is, almost 52% abundant. So the most abundant isotope is 208. So the weighted average is going to be closer to the heavier isotopes than it is to the lighter isotopes. Okay? And so when we do the math, we get 207.2118. So 207.21. Most periodic tables have lead as 207.2. So if you just said 207.2, that's fine. But again, our usual rule is to go to 2 decimal places. And again, don't forget the unit atomic mass units, okay, AMUs. Okay. So here, number 4, we're doing the same thing. So the mass number, remember, in symbol notation, the mass number is the number in the top left-hand corner. So this is hydrogen with a mass of 1, hydrogen with a mass of 2, hydrogen with a mass of 3. So we do 1 times 0.99 plus 2 times 0.008 plus 3 times 0.002, right? That's how we would calculate it. So there's my setup. The average atomic mass equals 1 times 0.99 plus 2 times 0.008 plus 3 times 0.002. We do the math and we get 1.012 AMUs. Again, most periodic tables will have it written like that. And that's what we got. Okay. So here we're doing the same thing. So we got titanium 46, 47, 48, 49, and 50. So the only annoying part about this is we got 5 isotopes. So it's, we got to do this times that percent, that times that percent, that times that percent, that times that percent, and so on, and then add them all up. All right. So again, it's not that difficult once you know what you're doing. It's just basically plugging in check. The mistakes that come are, not putting the decimal or the percent in decimal form the correct way, or just miss, there's a lot of digits going on. You're punching them in your calculator. You might hit 9 instead of 6 or something like that. So, a lot of room for human error, but the main thing is just understanding that thing. But you can check yourself a little bit, because if your answer, again, for titanium, if I have a range of isotopes ranging from a mass of 46 to 50, then my average atomic mass has to be between 46 and 50. If I get a number that's above 50, well, I did something wrong. If I get a number that's below 46, then somehow I did it wrong. If I fall within the range and I'm close to some of the more abundant isotopes masses, then I probably can be satisfied that I did it right. But if you're not close, if the average that you calculate is not closer to the more abundant isotopes, then maybe that's another red flag that you did something wrong. Okay. So when we do that, we get titanium 47.92 atomic mass units. Okay. And then here, number 6, number 7, we actually solve for it. So now we're given the mass number and we're given the average atomic mass, and we want to be able to explain what that means in terms of percent abundance. So we're told that silicon has 3 isotopes, 28, 29, and 30, and the average atomic mass of silicon is 28.086. And what does this say about the relative abundance of the 3 isotopes? Well, that's just screaming that silicon 28 is clearly the most abundant isotope. Okay, almost as abundant as like carbon 12 is as carbon's isotope, right? Carbon is 12, 13, and 14, and its average atomic mass is 12.01, and that's because carbon 12 is around 99% abundant. So silicon 28 isn't going to be 99% abundant, but maybe 97% abundant. right? So, so it's telling us isotope 28 is the most abundant by far, and then there's very few amounts of 29 and 30. We don't know which one is lesser abundant, 29 or 30, but they're both going to be very small numbers, okay? So again, it's just based on the fact that this average is weighted on how much X is, how much Y is, and how much Z is. And because this number is closer to 28, I know that the percent abundance for 28, for silicon 28, must be the most abundant. So most silicon atoms are going to be silicon 28, and there's going to be very few silicon atoms that are 29 and 30, okay? All right. And then the last one here, we got two isotopes, right? So we got an element that has two isotopes, and we're given the average atomic mass. So given the mass number of each of the isotopes, and given its average atomic mass, now we want to calculate the percent abundance, okay? So this is going to be using, I don't know if they still call this in math, but it's going to be kind of equation systems or systems of equations. So the first equation to use is the average atomic mass. So we know that average atomic mass equals the mass number of isotope 1 times its percent, which is an unknown, so I have it as a variable y, and then the other isotope's mass number times its percent, but that's going to be x. That's also going to be unknown. Now, if this were right in the middle, if this were right at 152, and so notice I got a 151 basically isotope, and I got a 153 isotope. And if the average atomic mass was 152 even, then that would tell me that it's probably 50%, 50%. It's almost a 50-50 split here, almost. But it's a little bit less than 152. So that's telling me that this isotope is probably a little bit more abundant than this isotope. So when we figure out X and Y, I bet this isotope's percent is going to be a little bit above 50, and this is going to be a little bit below 50, okay? But we can solve for it. We can figure it out. So this is one equation. But then we have to understand, how percents relate to each other. Remember, all the percents have to add up to 100, but that's when they're in their percentage form. But when they're in their decimal form, they add up to 1. So whatever X and Y are, they're going to add up to 1. So we have two equations. They both have two different variables in it, X and Y, okay? But we can figure out what X is and Y is using the equation system, right? So what I'm going to do is I'm going to take this equation and I'm going to solve for Y in terms of X. So I'm going to take this equation and I'm going to get Y on its own side. So I'm going to say Y equals 1 minus X. So instead of putting Y in this equation, I'm going to put 1 minus X there instead. So now I have the average atomic mass that they gave me, the mass number times 1 minus X, plus the mass number times X. So anytime you're given a question where they give you the masses of each isotope and the average atomic mass, and you're asked to find the percent abundance, make one of the unknowns 1 minus X and make the other one X. Now, if you want to save yourself some, if you make mistakes mathematically when you're doing stuff with negative numbers, then make the heavier isotope X and make the lighter isotope 1 minus X. But it really doesn't matter which one you call X and which one you call 1 minus X, just as you understand that in this scenario, I'm calling X the percent abundance for this isotope. So when I solve for X, that's going to be the percent for this isotope. And then 1 minus X is going to be the percent for that isotope, okay? If I switched it, I got to make sure I remember that, right? Okay. So you got to do the math, you got to combine like terms, all that stuff, right? A lot can go wrong. But the way I have it set up here, you should end up with X comes out to be 0.51986209, okay? Now remember, those were percentages in decimal form. We have to report the actual percentages. So how do I turn this into a percent? How do I turn it back to a percent? Multiply by 100. So that means X as a percentage is going to be 51.99%. Okay? So that means the europium 153 is 51.99%. How do I get the other percentage? Subtract from 100. So 100 minus 51.99% will give me the percent of the other isotope. Okay, so there you go. All right. Okay, so that's, essentially how you calculate average atomic mass and what, all that stuff means, basically. So hopefully that gives you a better understanding, and you can, do your Schoology assessments and all that stuff. With that in mind, especially if you're getting that one question wrong, that's kind of like this this question on the worksheet, where you have to actually calculate the percent abundance. Remember, I'm never going to give you a question like this where you have three isotopes or three or more isotopes where you have to calculate each percent abundance. But what we will do is two isotopes. So you get the mass number of each isotope, you're given the average atomic mass, you have to use that to calculate the percent abundance. So remember, make one of them X, make the other one 1 minus X, and that's how you do it, okay? All right, have a great day.